Algebra 2, Lesson 61, Chemical Mixture Problems, Type B. Alright, now this differs from our original chemical mixture problem, whereas initially we would have two chemicals adding to a final solution, like we see in this cool diagram right here, where you have two different solutions creating a final solution. In this case, what we're going to be having is a single solution losing a certain amount. So they'll be losing it through evaporation, or it'll be poured out or something like that. So it's essentially the same thing, but in subtraction as opposed to addition, and we're only given one solution to start off with. So in our practice, they tell us, they ask us how much water must be evaporated from 400 gallons of a 15% saline solution to get a 40% saline solution. So we're going to do the same thing we did before. We're going to represent our equation in terms of volume, and then again in terms of percentages. So for our problem, we'll start with the volume. They have 400 gallons of a 15% saline solution. So our starting volume is going to be 400 gallons. And we got to find out how much we're going to subtract from that 400. So our starting, and then our evaporated minus evaporated, to equal our final. And this is actually a really interesting equation because it's really hard to wrap your head around first. But all we have to do is, when we write this, we have 400 minus our solution evaporated is going to equal our solution final, right? But the final solution is equal to this quantity right here. So 400 minus solution evaporated, or 400 times our starting solution starting, minus the solution evaporated, is going to equal 400 minus solution evaporated. Now, this looks like the exact same problem on each side, and right now it is. So the distinction that we make here is, when we write this, we're going to put the left side, each term will be in its own set of parentheses. So the first term, instead of solution started, it'll just be its own parenthesis of 400, since we know what it is. The second solution, the evaporated, we don't know, so we'll separate it in its own parenthesis. And then the right side, since it's all one idea, we'll enclose it. So this is one number, and this is now two numbers. So that's the first thing that you have to wrap your head around, is this weird, messed up notation, because it's hard to figure out the equation, especially when you're starting off. So just remember, your starting amount minus the evaporated or whatever is poured out, the left side would be two ideas or two parentheses. So we're dealing with two ideas. And then the right side, or the final, is one idea, so it gets put in one parenthesis. Now let's go back to the problem. They tell us we have to represent this now in terms of percentages. And they tell us that the 400 gallons is a 15% saline solution. So the second equation, we'll do our working notes over here. The second equation, we're going to have 0.15 times that first idea of 400. And then the amount of water being evaporated, that's not going to have any saline solution at all. So it'll be 0.15 minus the solution evaporated, and then that's going to get a 40% saline solution in the end. So our final solution is going to be 0.40 times 400 minus SE. That's a little small, so we'll multiply this all by 100, and then I'll rewrite it. So when we multiply this by 100, this is going to become 15. This is actually going to become 100, and this is just going to become 40. So I'll write that a little bit neater over here. So what we have is 15 times 400 minus 100 solution evaporated is going to equal 40 times 400 minus SE, or solution evaporated. So this is our equation written in terms of volume. This is our equation written in terms of percentages, and we've accounted for the decimal, so that way we're working with whole numbers. And that's where that 100 came from. I'll simplify this equation so that way I can substitute or eliminate between them. So 15 times 400 is going to become 6,000 minus 100 SE, and then 40 will distribute. 4 times 4 is 16. Add the 3 zeros. It gives me 16,000 minus 40 SE. Now, I actually don't even need to substitute or eliminate in this problem. From here, I can just solve one of these equations, and then I will know the amount of solution that's been evaporated. And you know what? I might have wasted a little bit of time doing this second equation, because now that I think about it, we don't really need to deal with the percentages. Or maybe we do. That's right, we do. So the reason we didn't waste any time, sorry, I just had a little moment of logical thinking. So the problem with this top equation, since we're only got one unknown, is if we try to solve for this top equation, we're just going to end up with 0 equals 0. See, if I try to add SE to this side and I add it to this side, that's going to cancel. And then if I subtract 400 from this side and minus 400 from this side, I end up with 0. So this equation is good to help us, but we can't use it to solve. We can use this equation to solve since we've accounted for the percentages in the solution. So I'll go ahead and move all the SE's to one side, and I'll move all the volume amounts to one side. And what happens is I get negative 10,000 over here, and then over here I get 60 times the solution evaporated. So I finish solving, and 1,000 divided by 6. So the solution evaporated is going to be 1,000 divided by 6. 6 goes into, I'm having a tough day mentally here. Let's see here, 1, 4, 6 goes into 40, 6 times, and then we're just going to keep getting a repeating 6. So the solution we need to evaporate is 166.6 milliliters. Alright, I hope this was more helpful than confusing for you. The key thing here is writing that first equation and 2 ideas and 1 idea, then using that equation and adding the percent values. Once you add the percent values, you can solve the equation and find out the amount that you need to evaporate. And that's all there is for this lesson.